has nicely gotten the thing here. Go away. Let me hit on the slideshow. And why are we going automatically here? All right. This is basically a discussion of NASA missions I have personally worked on in some fashion. There have been, of course, many others that I have not been involved in. Some, not covering everything, most of the ones that actually involved astronomical work. I work at the Glenn Research Center, Lewis Field. It's originally one of the NACA, the National Aeronautics Advisory Committee, or actually National Advisory Committee on Aeronautics. It was opened just at the start of World War II. We specialized in aircraft engines back then, and we are still the NASA center that is involved in studying aircraft engines. The hangar is there because we have a taxiway directly to Cleveland Hopkins International Airport and fly research missions out of there. In fact, somebody you've undoubtedly heard of started his career with NASA, actually with NACA, flying planes from the hangar. Neil Armstrong was actually hired to do that. And who hired him, although that guy is now deceased. And I was saying about vacuum tubes, well, mostly I worked on traveling wave tubes. And this is a schematic. You've got a heater that heats the cathode that the electrons go off from. They're accelerated. And then there's a helix, generally, that slows the RF circuit down to pretty much match the same speed as the electron beam. And the energy from the electron beam is converted into RF power. And they typically are 40, 50 dB of amplification. That's 10,000 to 100,000 times amplification. I particularly did a lot of work on the collector, which recovers the energy because the beam still has about 90% of its original energy when it finishes amplifying. So you want to recover as much as that. The top efficiencies we've achieved on fairly high power tubes are about 69% efficient. They are for 69% of the DC power put in. And one of our tubes we worked on was one of the tubes for Cassini. This is actually a picture of the Cassini spacecraft before launch. We basically bought the Ka band tubes for Cassini, and actually were involved in deciding the power supplies for both the Ka band and the X band tubes at Cassini. And I found out many years later that I'd actually worked on designing the collector for the X band as well as the Ka band. They just copied the X band, the Ka band collector for the X band. Reached Saturn orbit July 1st, 2004. The Huygens probe landed January 14th, 2005. And on September 15th, 2017, fuel was running low. So to make sure it didn't crash into one of the possible moons that might hold life, they deliberately sent it into Saturn. And the tubes I worked on were still working all the way down. And these are the namesakes of the satellite. That is Cassini 1. He was hired to be the founding director of the Paris Observatory. And his son succeeded him, and a grandson succeeded his son, and a great-grandson succeeded him as the fourth director of the Paris Observatory. But about the time of the French Revolution, so he spent some time expecting to be guillotined. So his son became a botanist. Decided that was safer than astronomy. Huygens was more of a Dutch one. I know the latest SCaN Telescope had an article on Cassini, and Huygens was rather amazed that Cassini was out observing the sky every clear night. This is a composite picture taken by Cassini. of the inner solar system in Cassini. Mars, Venus, and Earth and Moon sort of show up there, but not very well. The pointers show them dots that correspond to each one. This is actually the K-band 32 gigahertz traveling wave tube amplifier we did. The tube is that little yellow brass thing on the side. The black box converts the low voltage DC power that the satellite has. The traveling wave tube uses a few thousand volts and quite a few different voltages as well for the collector and other items. And we actually later on mailed lighter ones at much higher power, but this was an early one, but it was still 10 watts, and the previous record holder was 3 watts. So a big advantage on that. One of the things that was used for was testing general relativity. What they did was send signals up at both X band and Ka band, and then they relayed them back down. The X band signal that had been sent up was relayed both through the Ka band tube and through the X band tube, while the Ka band signal was relayed just through the Ka band tube. This is because the electron density has different delays effects on signals at different frequencies. So let's let them cancel out electrons in the solar atmosphere and wind. And you have very accurate measurements. They tested general relativity, the signal delay due to the sun's gravity well, and they also searched for gravitational waves. They'll use this for measuring the mass of the planets, some of the moons of Saturn, and even higher moments of the things. They could tell the tidal deflections on some of the moons, by how much the tidal changes from Saturn occurred. And the higher moments also let them tell things about the structure within the planets. They made atmospheric measurements during occultations of Saturn and of its big moon, ionospheric measurements during those occultations, and also measured the diffraction characteristics of Saturn's rings. So the two radios were used for quite a bit. There actually were 3 frequency radios on. The main data radio was at X band. The K band tube was used simply for radio science measurements. And there was also an S band tube that was for command and control, but also used in radio science. The general relativity effects, they consumed the geodetic effect to within 1 part in 50,000, 0.002 of 1%. And they measured gamma to differ from 1 by less than 1/40,000th. Now, this was the time it was, it said that Cassini was able to see much lower frequency gravitational waves than the LIGO ones are. I mean, much more that they were frequency from more of the hour range versus hertz. And it's still the most sensitive ones for ones in that frequency range. I believe there's now a thing with quasars that is looking for even lower frequency gravitational waves and may have detected some. Cassini did not detect any gravitational waves. It wasn't really expected to, and their best theory of how much power is that frequency, how low frequency gravitational waves, that low frequencies are probably not going to be detectable until much more sensitive equipment is available. They measured some measurements on Titan's crust, looking for gravitational anomalies, how they corresponded to the height anomalies. If it's weak ice that's isostatic, you'll see a positive gravitational anomaly because that ice is partially up closer to the satellite than it is. So you're actually moving it the way the average ice thing closer. If it's rigid ice, you'll have a small positive one. I believe they actually saw more of the negative gravitational anomaly with rigid ice but with surface erosion. And they actually saw quite a bit of surface erosion in the radar measurements they made of it. Atmospheric occultation, basically the technique is they keep close track of the phase of the signal. They remove the astrodynamics to remove the effects of the spacecraft distance to the Earth. And the extra effects are due to bending, which depends on refraction. And it's possible to derive profiles of temperature and pressure. Abel inversion is actually a way of converting from the linear measurements to a spherical distribution. And that was named after a Russian mathematician that developed rather earlier than necessary for the mission. It was, I believe, in the late part of the 19th century that he developed the inversion. And this shows basically the things that are happening here and how it varies and sees. The results for Saturn's atmosphere. This is actually a fairly typical atmospheric thing. Down at the bottom, you see the part close to the satellite, close to Saturn. And it's basically a convective atmosphere, so the temperature drops with altitude. Because you expand, the gas expands, it cools off. And it basically has to cool off at the right temperature. If it cools off too fast, it would sink down and you wouldn't rise. If it cooled off too slowly, it was still warmer. It would keep rising and mix the atmosphere. Then you hear a plateau, very similar to the Earth's stratosphere. And up above that, you get an area where the atmosphere is heated by ultraviolet and X-ray radiation from the sun. And it's a very thin atmosphere at those pressures. So it can be heated quite a bit, quite effectively by the sun's radiation. It doesn't easily cool off. So that is like the thermosphere on Earth. And the pressures are different, but this is very similar to the things here. Very similar to results on Earth and similar to the other planets that have been observed. In the ring occultations, they look at the phase and amplitude of the signal going through the ring. Direct coherent measurement can reveal radio structures and give some size distribution information because of the use of all three frequencies. So the lower frequencies are not scattered as well by small particles. Those really small particles don't are very effective at scattering any frequencies. They're particularly effective when the particles are about the size of the radio frequency. And you also can tell things about the bulk motion and meter size things by looking at the part of the signal that is not coherent by scattering on the systems. And this is an image derived from those results. The white band has such density that it blocks two of the three signals, so they can't really make any size distribution measurements. They can't really distinguish between how dense it is and what size the particles are. The purple particles are particles that are greater than 5 centimeters, and thus they're not much X-band or the Ka band signal because they're much smaller than that. The blue is less than 5 centimeters. That has quite a bit of effect on the X-band, and not so much because it's still the Ka band signal is about 1 centimeter, and the X-band is about 4 centimeters. The green is the part that really affects the K band is the only one that is much affected by that. What's the area? So that's how they tell that the particles are small there. Now, it turned out that the had spare tubes at X-band left over from the Cassini mission. And some of you may have joined me in watching this. That was the Deep Impact mission had a large copper block it threw into Tempo 1, the periodic comet Tempo 1. And this is a picture from Deep Impact of the impact itself. The dust knocked off here was bright enough that I was my college in Gladwin, Michigan, and actually saw it. I remember for certain with binoculars, and I think with the naked eye, you could see the dust appear. From the Tempo 1 was too dim to be seen, even with binoculars, you saw a star near it. And then you saw this appear if the hit occurred. This was actually the night of July 4th, 2005. So it was sort of a 4th of July fireworks exhibition for us. And it's actually the furthest thing you could see with the binoculars or the naked eye that was ever done by men. And of course, all the big telescopes were also looking at that and taking measurements. This was a pre-impact picture in the impact itself, taken after it hit. You lose all detail, of course, in the dust. But NASA tends to reuse satellites. And the Stardust was one that gathered interplanetary dust on glass plates. And after dropping the glass plates off in Earth, mute your mic, please. It was redispatched to look at Temple 1. It flew by actually on Valentine's Day in 2011 and took a picture of the crater. So you can see it actually had some effect on the surface, but fairly small even for the large cloud of dust. And as I said, they reused satellites. So after Deep Impact was still going, so they used it to flew it by Hartley 2, another periodic comet, to take pictures of it. It was also used in an epoxy continuation where they used its camera in much the same way that the Kepler mission was used. They just constantly stared at the same portion of sky for variations in the light. Another mission I've worked on that's still orbiting the moon and still in operation is the Lunar Reconnaissance Orbiter. This one I basically was involved in buying the tube, which was a downscaled version of one we had developed for missions probably to Jupiter under very high propellant. I was going to be a 32 gigahertz, 250 watt tube. The Lunar Reconnaissance Orbiter needed a 26 gigahertz tube at 40 watts. So we developed, it was done largely in parallel with the 32 gigahertz, 35 watt tube being developed for Kepler. And this is the traveling wave tube. Actually, two of them, we bought a spare at the same time. That's to make sure we have one that actually is ready to fly. We flew the better one and kept the other one on the Earth, basically to use for comparison if there are any problems or such going up. This is an elevation map. One of the items on ILRO was a laser altimeter to make measurements of how the surface of the moon varies. So you can see there's about a 20,000 meter variation from one part of the moon to another with various basins and such. This is the Hain crater. It's near the South Pole. Here's an impact melt tongue from a crater. And the crater created a great deal of molten rock that then flowed down the slope of the slope. Here is a picture of a ray, very fine detail. You can see there's a lot of boulders in the ray, actually much more in the ray than outside the ray. This is the Apollo 1 landing center site. We picture the camera, the retroreflector from the Earth, the experimental package that included a seismometer, and the cover from the lunar orbiter, as well as the lower stage from the lander itself. That was a two-part one. The one part they flew it down, rested on it while it was on the moon, and then took the other part of the LEM back up to the command module, leaving the other part, which basically serves as a launch pad for the thing. They also pictured the other NASA landing sites, and they actually the Russians landed a couple of rovers that have retroreflectors on them. So they're very interested in finding out more detail where exactly those were, so they can determine just where they're getting those reflections from the moon, just where those are relative to the moon center. It also, as part of the thing, photographed LADEE, the Lunar Atmosphere and Dust Environment Explorer, a small satellite that was launched later on and traveled closer to the moon. So they managed to image that. This slide here shows an alternation between the picture itself and that artist model of the satellite, LADEE. LADEE has since crashed into the moon, but LRO continues to run the experiments and studies there. It has a neutron reflectometer that was actually supplied by the Russians that's used to look at images from that. Besides the wide field and the narrow view cameras, high definition camera there, it also has a camera that operates in Lyman alpha radiate light. This is a deep ultraviolet light that scatters very effectively off of hydrogen because it's the first excited, from the ground to the first excited state of hydrogen atoms. So it basically is a fog of Lyman alpha radiation throughout the inner solar system, which helps you if you're trying to see places that aren't directly exposed to the sun. As I say, it continues in use. It is a picture from the other side of the moon of the Chinese Chang'e 4 and Yulu 2 rover that are currently operating on the far side of the moon. And there have actually been several, and they see the rover is traveling around. The Israelis had a lander. There were some problems with it. It forgot how far away it was from the moon and turned off its retro rockets too soon. So it sort of impact, it leaves another small impact crater on the moon. Later on that, I worked on the SCaN Testbed. This is shortly before launch. We actually started building a third tube for LRO in case there was a problem with one of the first two. And that was around, so we actually used that on the SCaN Testbed. And this is the SCaN Testbed on the International Space Station. It was there for a couple of years doing communications experiments. Later on, it was brought off in one of the one of the supply modules that burns up on reentry. So it is no longer around. It's been replaced by some other experiment. And I also worked for a little while on Gateway's first element. The power and propulsion will be based on the Maxar 1300 satellite bus. It will go into what they call a halo orbit. It's not exactly around the moon because part of the time it's actually more under the Earth's gravitational influence than the moon. But it's sort of an Earth-Moon orbiting, although it stays closer to the moon than it ever comes to Earth. Once it's actually up there. Nowadays, they're actually going to launch the halo, the human habitation part along with it. We'll launch together with the Maxar. This is the part that has the propulsion and power elements, so it will lift that into the halo orbit. And are there any questions?
Great, thank you very much, Dale. We really enjoyed that. Everyone is muted at the moment. So Bob, will you unmute people so they can ask questions?
Okay, give me a moment here. We'll see how I can do that.
You can also unmute yourselves, I believe.
Yeah.
Dale, I have one question. This is John.
Mm-hmm.
On the TIPL-1 impact mission, did that impact, was it large enough to have any negligible effect on the orbit of that thing?
I don't believe it was large enough to do that, although it hit at very high speed. It was only about 100 kilogram copper block that they flew into it.
Ah, okay. All right. Okay,
it was, however, actually visible from Earth. I remember going out to look at it. At that point, I hadn't actually found out. I actually found out later on when there were some questions about the tubes on the epoxy continuation mission, that I called up the person that managed that, and he told me, "Oh, did you know that you designed the collectors for that?" I hadn't realized they'd be used by design for the X-band tubes.
Dale, you spoke of the Temple 1 impact. About how far away from Earth was that object?
I'm not really sure. It was near perihelion, so I think it was probably about an astronomical unit, but I'm not really sure just how far.
Okay.
Probably should look that up sometime.
Well, I was just, with the further the distance, the harder the target to get out there. The guidance just has to be incredible.
Yeah. The deep impact satellite did finally break down. Turned out the thing they had, that the problem with the TWT was the satellite, this was an earlier problem they recovered from. The satellite had gone into safe mode for some reason, and it shuts down that system for data communications. But they got it back up and lasted several more years. But they did finally lose contact with it. They don't really know what happened.
Right.
Excuse me just for a second, Bob. I think we're unable to unmute everyone en masse, right? So you'll have.
I don't see a function for that. You can
Okay.
ask them to, you can mute all, and you can ask them to unmute themselves, but
Yeah.
I don't see.
Yeah.
an
Okay.
unmute
Sorry
all.
for the confusion. If you'd like to ask a question, then please unmute yourself, which you can do along the bottom of your screen if you move your cursor down, at least on a Windows machine. It's on the lower left.
Yeah.
While I have you, Dale, I do have a question from the gentleman who gave us the presentation for our last meeting. Was about missions to Venus. I think that was the actual title. And he thought he was going to make it here tonight. But he said he believes that the Glenn Research Center is working on new missions to Venus. And I wondered if, if that's true, or if you could enlighten us on any of that.
Definitely. I've actually worked with some people who are working on silicon carbide electronics for high temperatures. And one of the two areas that they're working on particularly are missions to Venus, because their electronics will be able to operate on the surface of Venus. The other reason that they're being funded is working measurements inside jet engines, which is another area we work on heavily. We actually say that our center is located very well because one of the things we work on is quieting jets for takeoff and landing. And one of the takeoff patterns is right over our center.
Oh, so that's a good test for you then, I guess.
It's like, we have a real motive here.
Okay, all right. Thank you, Dale. Any other questions? Feel free to unmute.
Actually, one thing there for the Venus mission, we've also built a machine. We also have a chamber for testing at Venus surface conditions.
Okay, I believe he did mention that. I think he had some sort of photo of that as well. Okay.
Yeah.
Right,
I haven't been that directly involved, but I have heard some of the results every now and then.
Okay. Okay, great. Thanks, Dale.
Do you test the engines on that site? Any of these products, are they all done out on the desert?
Well, there are two types of engines. We used to do testing on the center for rocket engines. I know I worked with a guy who had done that. Well, I started actually working, I think, on propeller engines and then to jet engines. The center was open in World War I. We were working on propeller engines back then. I think he started on jet engines and worked on rocket engines for quite a while. Those facilities have been eliminated. We have a subsidiary facility near Sandusky. If you were by Sandusky on the expressway, that thing that shows up near the expressway, it looks like a reactor chamber, is actually the world's largest vacuum chamber.
Oh, okay.
We can actually test upper stages of rockets. They often use that for testing the release of the canopies they have around the rocket with satellite before they launch it. Because they've lost quite a few satellites that those things would not release.
Well, It's important.
So that's one of the things
Oh.
they can test. They can also test rockets and such under the full volume of sound. We have like the loudest speaker system in Ohio and probably one of the largest houses in the world, because rockets make noise that make jet engines sound quiet.
Yeah.
That was what I was getting at.
And there's actually a facility that was originally developed to test, and still used to test upper stages at equivalent of altitudes that like 80 to 100,000 feet. It can pump down hard enough to keep them at the altitudes equivalent to that while they're firing a Centaur engine or such. That's for tests because they operate in the atmosphere and higher. And you therefore have to test them basically in a vacuum, or at least at very low reduced atmosphere. We have that. We can actually test rockets on the ground for that out at the Armstrong facility.
When you say Sandusky, you mean in Ohio, right?
Yes.
Okay.
Mm-hmm. Yeah, it's actually out near the near the turnpike as you're going by.
Right.
So how large of a staff does the Glenn facility have, roughly?
Between contractors and NASA personnel, there are about 3,000 total. Plumber, actually, I'm still calling it Plumbrook. It got renamed early this year. It is now the Neil A. Armstrong Test Facility of the Glenn Research Center.
Dale, do you have anything on the James Webb Telescope?
I don't have. I just get basically the information that they put in the various news bulletins on that one. So just basically the standard ones. I know there was talk about testing some of the material at, well, it was how you got something there. A C-5 could fly it in to Mansfield, but it would take 2 days by road, and they'd have to raise a couple of railroad bridges to get it under. I actually discussed the possibility of flying it in. Cleveland also has an airport on the lakefront, and taking it by barge most of the way to Sandusky, and then by road. But I think they finally found a facility at Johnson they could barely fit it into for test.
So you do nothing at Wright-Patterson anymore?
We have some work. We do some work with Wright-Patterson. That's probably more directly our aeronautics people that work with them directly. We also do some work with people at Kirtland Air Force Base, which is more involved in the communications and such.
Yeah.
Used to be Rome, but they moved it from New York to, I think, New Mexico is where it's at now. And we also done some work. We do communications work, so we have test facilities at various parts of the world. I know some more people installed a radio antenna at Sublard in Norway, except it's not in mainland Norway, since the island's a long way north of Norway.
What about White Sands? Is that active in anything at all?
That is actually where LRO sends all its information down to.
Really?
It's close to Kirkland.
They have three towers there. They're identical. One for the Solar Dynamic Observatory, one for LRO, and one spare.
Okay.
And we've also been work with West in some of the areas down there on optical communications.
Okay.
They don't get blocked anywhere as much as they do in Ohio.
What do you know?
And actually, we've had some of our aeronautics radio. I've done aero communications too. There we have had to move things down to Mansfield, Ohio, because Glenn is actually so close to Canada that we have to get Canadian approval for using radio experiments here.
Okay.
We do a lot of testing here on icing too. We have the icing tunnel. We can freeze things. Their motto is "We freeze to please." And as far as testing jet engines, we do that at Glenn. Usually the office building I usually work at is right across the road from the test facility. They can test any jet engine in the world at altitude, even with its afterburner going at full thrust, at simulated altitude. And they recently added a facility there. I did a little bit of work on that. One year, they said, you're a COR, you can handle some of the jet engine contracts. So one of those was, there was a jet engine that had flamed out over Canada. And they had good information on what the weather was like there. We've now added a facility that had high ice water content, well, sort of a combination, very wet ice, and can be dumped into a jet engine in our test facility. They were measuring everything. And they put the jet engine that had flamed out a test facility after putting a lot more measuring stuff on it and ran it. And it was a very successful test. And we also did a lot
White
of
Sands,
work.
they sometimes have to get permission from Mexico if they're testing communication equipment.
Yeah. Because you get too close, your RF can overlap. They knew though there was. Oh, we also did a lot of, my friends did a lot of work. We had a thing for throwing things well, it's basically designed to do test aircraft parts to make sure they can handle things getting smashed into them. But he also did a lot of work and had a very nice presentation overall on the Columbia mission to find out what happened there. And he's got all the nice films when they fired little pellets of foam at the parts and they exploded, leaving big holes in the parts. So quite a bit of that work was done after the mission collapsed. Although one of the experiments that flew on Columbia was developed, we have a considerable microgravity group. And they knew a lot of the people that died on the mission. And amazingly, recovered some of the recorded information from the wreckage.
Any other questions for Dale? Going once, going twice. Well, great. Thank you very much, Dale. We really enjoyed it, and we really appreciate you coming and giving your presentation. I know it's been a long time coming. I think last fall is when we first contacted you. So thanks for sticking in there with us. And we hope to talk to you again sometime.
Yeah.
Yeah.
I
Thanks.
actually may drop in on some of your later ones there. Some of them sounded interesting.
Oh yeah, we have several NASA people. Try to make it to the Stargaze this year.
I will.
That would be great. Maybe we could hook you up to be a speaker there.
We
That'd be
can
quite
give you
possible.
the dates. We can give you the dates for that right now if you hold on a second.
All right.
Yeah, somebody has to look that up.
That is September. The 9th, 10th, and 11th. That's Thursday, Friday, and Saturday.